Hi guys, my name is Dunya HAAKE, and I hope you guys doing alright. And I'm here to talk about the article that I chose for this presentation. If I talk about this article was written by these amazing people from China. They actually from the University of Science and Technology on East China. And these articles here mainly talk about how the forming of low density polyethylene with carbon dioxide characterized. So they used high pressure rheometer to identify their crystallization behavior. So as you can see, my main concern about this article is about high pressure rheometer. Now let's talk a little bit about the introduction and how they actually involved into this kind of studies. So in this case, I'm usually concerned about the plastic, a type of plastic actually, which are foams. We all know foams. Usually foams take a majority of part in industry. Among them, there is a there is a plastic foam called semi-crystalline plastic foam that includes three main polymers, which are low density polyethylene, polypropylene, and polyethylene tetraphthalate. These are more famous in industry because of their crystal behavior, especially polyethylene is a good example for that. And also they have a low density, which makes them a good chemical resistant, good electrical properties, and also they're low cost. So when we move in more into the background of testing these crystals, rheology plays an extremely important role when it comes to polymer forming. So these are some good factors that would enhance the polymer forming. So high saturated pressure, low temperature, loss factor, crystal formation, shear, and or extension flow. These are the items that would enhance the polymer forming, like I said before. So we need to understand a bit more about loss factor here to understand this article a bit more. So this is a good graph to understand how the loss factor actually affects on polymer forming. The factor of loss that would given by the ratio of loss modules to storage modules is going to define how well the forming process will occur. So if we get a gradient on this graph, it is G star going to be equals to G double dash over G dash. So G double dash actually represents the loss modulus, and G dash represents the storage modulus. So if the loss factor is low, which means when the storage modulus increase, that increases the forming process. So when the storage modulus increases, the loss factor actually going to go down. So the lower loss factor is going to be enhance the forming process. So when the loss factor goes down, the forming process is going to go higher. And other than that, loss factor is a good example for forming forms. And also other than that, higher saturated pressure and low temperature, and also formation of crystal also increases the forming. So since I mentioned the crystal formation, how the effects on the forming process, I'll talk a little bit about low crystal, how crystal formation effect on forming process right here. The crystal act as a heterogeneous agent that can improve cell nucleation, which will maintain form structures due to increase of the storage modulus. So as we talked before, increasing storage modulus improve forming. So these all factors come right back into the loss factor right there. And in this experiment, we'll be using these instruments to identify the crystal behavior. And I'll be considering more about the HP rheometer, which is the high pressure rheometer. Other than that, in this experiment, What they want to learn about is that the forming of low-density polyethylene with carbon dioxide. Dissolving gas into crystalline is not easy. That can lead into non-uniform bubbles in foam, so there is bubbles in foams gonna change the whole structure of the foam. So in ancient time, there were scientists actually been working on these kind of things. A scientist called Park et al. Hoping that I'm saying the name right. Investigated how the shearing influenced dissolved carbon dioxide on the crystallization for branched polymers, which will also be used in this experiment in the future slides. Furthermore, there's another scientist called Lee et al. Lee et al. Found out that they can form crystals in lower temperature in lower amount of time by using high pressure DSC, which is a high pressure differential scanning calorimeter, which will also be used in this experiment. Let's talk a little bit about the instrument they used and why did they use it. So the first instrument that we're talking about is the HP Rheometer, which is our instrument that we're going to be talking today. The exact rheometer they used is the HAAKE Mars 3 HP rheometer, and this is an exact picture of that instrument right there. And it's a pretty nice instrument actually. And they also used high pressure differential scanning calorimeter for the crystallization kinetics, and this is a picture of that, and also a scanning electron microscope. It's pretty big considering it's a microscope because it connects with all these other parts. And also XRD, X-ray diffraction instrument. In this particular experiment, they use the wide-angle X-ray diffraction. Like I said, they use the HP rheometer for dynamic measurements to follow crystallization behavior by monitoring the storage materials and in various viscosity rates, temperature rates in certain atmospheric conditions. So in this case, what they did was they use a modified high pressure rheometer. We will be discussing it when we discuss the experiment later, under compressed carbon dioxide in between the pressure range of 0.1 and 28 megapixel. So it's a little bit high pressure. And I think these instruments are pretty typical to this field, such as plastic industries, of course, and agriculture fields as well. The only special thing about this experiment is that they modify this instrument a little bit, like I said before, when they do the experiment. Let me talk a little bit about the instrument right here. So this particular instrument, which is the HAAKE Mars 3 high pressure rheometer, I'm not sure if I'm saying the name right, maybe it's HAAKE. I'm not really sure. This specific instrument is suitable for all industries and has a specific industry accessories for polymer, petrochemicals, paints, coatings, inks, and such. And this instrument actually uses in pharmaceutical and cosmetic industries most of the time. This is a device uses to measure the way in which liquid suspension or slurry flows in response to applied forces. This particular device got interesting accessories like temperature modules, measuring geometries, and application for focused measuring cells. Basically, this instrument measures viscosity of analytical samples. Let me talk a little bit about each part right here. The module got a particular shape of edge. So as you can see here, there's a reason for this module to get a shape of an edge, because it balances out the active forces that forms from a sample and also the reactant forces that forms from the frame. So that's why it got that particular important shape of an edge. And if I talk about the first important part is the measuring head. Measuring head is this part right there. It actually helps to accommodate sample. I'll tell you where the sample goes in. This is where the sample goes in, and this is the spindle that immersed into the sample when the measuring head goes up and down. So this part, the measuring head actually can go up and down while the sample get into the sample holder, and the measuring head helps to immerse the spindle inside the sample. And let's talk about the lower mountain. This is not like measuring head, it can't move. It is a fixed, and this particular piece actually attaches the temperature control units and the module securely. Then the ergonomic control panel. This is like a keypad that got like 5 buttons. This actually controls the temperature here. And the other important part is the mounting rod. These mounting rods actually are running in the back of the instrument. These are for the temperature controls and test chambers. And this is the basic structure of instrument, and this right here represents the side cut of the measuring head. The measuring head right here, if we cut this measuring head into 2 side pieces, it's going to be look like that. Let me talk a little bit about some parts here that will be important to understanding. So there is a drop cap motor, which represents by the blue color here. That piece actually helped to it actually got a lowest inertia, so this will actually be helpful to get a faster response characteristics. So the next part that is important is the one axial bearing right here. As you can see, this is where the one axial bearing. It actually supports the motor shaft in vertical direction. And the next part is the 2 radial bearings. These are axles too, 2 right there on top and on the bottom. These actually support motor shaft in radial direction. And the final and the most important other part of this measuring head is the optical encoder. This actually enables of instant determination of a shear viscosity at very little shear rates. Like it actually helps to determine the shear rates of 10 to the minus 6. So that's a very little shear rate. So these are the important parts. Other than that, let me talk about a little bit of geometry. So like I said, this part right here represents the sample holder, and this is a spindle. So in the instrument, they call the spindles as geometries. So these are the geometries. So these geometries come in various sizes, materials, and with different surfaces. A standard one actually is made of titanium. They can be different shapes, like it can be either a concentric cylinder or a vein. It can be like a cylinder like that or a vein like that. Veins are used for high solids, while cylinders are used for fluids. now let's talk about what they exactly did to find out these relationships. They took LDTPE, which is the low density polyethylene pellets. Then they melting it to in rate of 1.8 gram per 10 minutes, and they compressed, they molded them under compression into circular geometry at around 160 Celsius under atmospheric nitrogen gas. So the diameter of the circular geometry came out to be 14 millimeter and 30 millimeter. The outer and inner diameters came out to be that numbers with the thickness of 2.0 millimeter. They also make sure they can obtain 99.99% pure carbon dioxide, and characterizes were studied under high pressure differential scanning calorimetry and high pressure rheometer. For the high pressure differential scanning calorimetry, what they did was they saturated the sample in 40 Celsius for 15 minutes and heated at 160 Celsius at a rate of 10 Celsius per minute for 10 minutes. So this is the amount that they're taking to make the sample. This will eliminate all the crystals and then cool to 50 Celsius at the rate of 2 Celsius per minute. That was for the high pressure differential scanning calorimetry. To identify the rheology characterizations, what they actually did was they actually modified the version, the regular version of rheometry actually. So this is a good picture of a modified rheology that they used. What they did was they put a support block. As you can see right there, the black one is the support block below the rotor with a gap of 2 millimeter. So the gap in here is actually the 2 millimeters. And this is where the sample actually goes in. Then they reduce the diffusion distance for carbon dioxide in low density polyethylene from 20 millimeters to 4 millimeter within the saturation time of 12 hours to 2 hours. So this experiment actually takes some time. So from 20 millimeters to 4 millimeters within that certain amount of time. The sample was loaded in the gap that I showed before, the 2 millimeter gap right there. It was loaded into the gap at the temperature of 150 Celsius. It was high temperature and different carbon dioxide pressures. And then they let it stay in that gap for 2 hours, so it would generate the homogeneous solution of low density polyethylene carbon dioxide with a mixture of carbon dioxide. Then the sample was quickly cooled to desired crystallization temperature and tested the storage modules we were talking about before, with an angular frequency of 0.5 radian per second. So once the sample was there for a certain amount of time, the rotor actually that rotates with the frequency of 0.5 radian per second. Then once the homogeneous sample was tested, then the forming process was tested by a scanning electron microscope. This is the exact microscope that they actually use. For the precision of this electric heating process during the forming, cooling water was cycled around the barrel. So there should be a barrel surrounding this rheometer around the barrel, and carbon dioxide is derived into cell via inlet and outlet. like this is where the gas go in, this is where the gas go out. In this case, it's a carbon dioxide. Like I said before, the cell morphologies of the formed were observed by using these particular scanning electron microscope. Finally, they used XRD, this particular one, the D8 Advanced Bruker one. They used it for characterize their crystallinity. Now, if I talk about the data that they got and what they actually discuss about the results that they got from the experiment. So they got this graph. Then the first one, it's the cooling curve of the melting of low-density polyethylene at a cooling rate of 2 Celsius per minute under nitrogen and carbon dioxide compressed in differential scanning calorimeter. So as we can see, the crystallization onset temperature and the crystallization temperature goes to low value with increasing carbon dioxide pressure. So this carbon dioxide pressure is higher than this carbon dioxide pressure right here, and this is going down. This is the crystallization onset temperature. I got shows right in the end of this each curve. And that's what that graph actually shows. And if we look at the graph next to it, that actually also a cooling curve that shows how the melting of low density polyethylene at a cooling rate of the same rate as it before. It was 2 Celsius per minute under nitrogen and carbon dioxide behavior in high pressure rheometer actually. So it shows when the temperature goes up, the storage modules goes actually down. And when you look at initial that in that phase, the storage modules increased and it was more linear as the temperature is low, indicating no crystals forms right here. And also the start modules decreased with increased saturation pressure. So these are the reason for this behavior of storage modules. So we actually talked about the storage modules in the first slide. And when we look at the next graph, the results of the next that they got, this is the next result. Figure 4 represents that how the storage modules behave with the time of a certain fixed temperature under different saturated gas pressures. So you can see the pressure of the carbon dioxide actually goes higher, and this curve represents the lowest pressure, while this one represents the highest pressure of the carbon dioxide. Under the in this case, their fixed temperature shows as at 110 Celsius. So like I said before, the theory of storage modules strikes again, and that is the main theory they used to explain the behavior of polymer forming actually. So when we look at the figure again, it shows how the storage modules, which is G dash right here, increased rapidly, and G dash right here, and increased rapidly, and then reaches into a relatively higher at the ending of the crystalline process. So after almost this point, it increases when the time goes up. So Sim may have heard about the induced time. So this is the induced time right here, but some may have not. So I'll explain what the induced time is actually. So the induced time of the crystallization is like it represents the time between our supersaturated solution reaching to the onset of nucleation. So as you can see, like I said before, when the pressure actually goes up, which is the this graph right here, the induced time is get bigger, while the graph right here represents the low pressure of carbon dioxide has got a low induced time. So we'll talk about what actually it means in a later slide. So let's talk about the pictures that they took from scanning electron microscope. So they took they actually looked at some pictures that shows the evolution of forming. So they made sure the condition of the parameters were the temperature was in 110 Celsius, and excuse me, the pressure of carbon dioxide was in 15 megapascal, and they actually point out what they did was they actually tested the relative crystallinity of the analyte at time of t. So when we look at the first three pictures, these percentages represents the relative crystallinity percentages. So they indicated that these first three pictures should show there is no crystal growth, since there is since the bubble size of bubbles increases, then it goes from letter number A to C. So they actually mention how there's no crystal growth, indicates in first few pictures, which was actually happened within 12 minutes under the conditions that I mentioned before. However, when the nucleation reaches into 49%, in the picture D, the crystal region shows a slowly making bubble diameter larger in some areas, especially at the interface between the crystals and amorphous areas. So they are actually shown in the crystal growth actually shows in the red arrows. Then when we move furthermore to the increased nucleation, the next three pictures that we're going to talk about is the E, F, and G. It leads into have a smaller bubble parallel with a larger bubble, as to show in 5E to 5G. And also this indicates that the density of cell also increase since the diameter of bubble gets low. So as you can see, the bubbles the diameters of bubbles get low as the size of bubbles goes down. And finally, in the final picture of the 100% of relative crystallinity, it shows there are no bubble shows, so there is no density occurs in the picture number H. So these so they can summarize all these pictures into actually three figures, as you can see on the right hand. So these figure 6 that's the figure number 6 in the article. They actually shows how all these relativity crystallinity effect on bubble expansion ratio in the first one, and the next one actually it's missing the y-axis. It should be the diameter relative diameter of each bubble, how it reflects with the relative crystallinity. It actually goes down, as you can see. As the relative crystallinity goes up, which means the percentage of relative crystallinity goes up, the diameter goes down. So since the diameter goes down, the cell density actually increases as the relative crystallinity increases. So these results show how the bubble sizes decreased with the increasing crystallinity. And later, to understand this a little bit more better, we can see the relationship between the storage modulus to the crystallinity between storage modulus to the crystallinity over time. This is the figure 7 in the article. It actually shows that the bubble size decreased with the increased crystallinity. End of each ending modulus shows where the forming process occurs. So forming process actually occurs at the end of each at the end of each of these modulus. So that gives all this information. So this is the picture representation of the graph on the left. And finally, this is figure 9. You can find it in your articles. It actually represents that how the crystallinity increases from 22. So the xt represents the crystallinity from XRD. These are actually XRD results. So this actually represents how the crystallinity increases from 22% to 43% when the relative crystallinity, which is the relative crystallinity as the relative crystallinity increased from 0 to 100%, and the crystallinity gives you by dividing the total area of crystalline peaks by the total area of under diffraction curve. So let's get into the conclusion of this experiment. So the first conclusion, they figure out the result. The results actually suggested that the crystallization rate goes down, which means it decreases with the increasing of carbon dioxide pressure. The next one, what they were able to conclude with was they also the temperature that the crystal nucleation occurs was also moved to a lower temperature under carbon dioxide atmosphere. Then they also figure out that the modulus, which is the storage modulus actually, they have various characterizations at 3 different regions. The first one is the modulus were regular at the crystallization beginning per time. The second one, then the modulus, the storage modulus increased dramatically according to the crystallization. And the last one, they were able to figure out that the modulus stabilizes at the ending of the crystallization process. After that, finally, they actually summarized how the foam behave with relative crystallinity as the bubble sizes decreases until relative crystallinity, which is the xt, reaches into 25%. Because of the crystal formation, then it lead to have smaller bubbles as the foam as the too much of crystal hold up the bubble growth. So those are the conclusions that they were able to make up from the article. And overall, I actually would agree with their conclusions from the results they got. They actually don't talk about the next step in this article, but I think it will be a beneficial. Actually, it will be like a nice move if you could actually do an experiment on how these forming properties behave in branch or long chain polymers under certain variable like temperatures, pressures. We can take the same variables that they actually took in this experiment. And I think that will be a fun experiment to work on. So this is going to be the last slide, and please, if you have any questions regarding my presentation I just did, send me an email to the email address mentioned above. And so here are my very interesting citations. So I'd like to have my colleague speaks now. So I will finish up by saying thank you for your attention.